When you examine premium streetwear, the first thing you notice is the extreme visual standard. We are looking at fine, multi-stage gradients, razor-sharp vectors, and highly saturated neon highlights that have to sit perfectly on a woven surface. If you execute these specific cyber-aesthetic designs using standard mass-market manufacturing methods, the result is a rigid, plastic-feeling garment that cracks after a few washes. A true premium t-shirt is an engineered system. It requires the precise alignment of three variables: fabric physics, pattern architecture, and printochemistry. These three variables operate in a strict dependency matrix. They rely entirely on each other to function. Changing a single variable, swapping in a cheaper synthetic blend, or using a standard cut, causes the structural integrity of the entire piece to collapse. Standard promotional t-shirts ignore this matrix because they are optimized for one thing: maximum cost efficiency at scale. A technical apparel consumer demands something different: structural volume that holds its shape, advanced breathability, and infinite wash durability. We are going to tear down this chassis to understand the exact mechanics of its construction. To understand technical apparel, we have to stop looking at t-shirts as fashion accessories and start evaluating them as engineered hardware. The foundational layer of this system is the base substrate, the fabric itself. Standard industry practice leans heavily on cotton poly blends to reduce costs and maintain everyday stability. But poly blends face a chemical failure when subjected to complex, heavy graphic prints. Because synthetic fibers are naturally smooth and non-porous, the ink particles pool and fail to bind securely to the surface. Switching to 100% cotton changes the physical interaction. Cotton has a naturally porous, textured structure. This porosity allows water-based inks and adhesives to sink in, anchored deep within the fiber, and achieve maximum color saturation. That deep integration is exactly what eliminates the cheap, shiny surface texture typical of polyester sportswear. Material type alone is not enough. The substrate also requires high grammage or heavyweight construction. If you apply a dense, multicolored ink layer to a lightweight fabric, the tensile weight of the graphic causes the material underneath to physically buckle, pucker, and warp. Heavyweight cotton acts as a structural barrier. It provides the necessary physical resistance to hold the graphic perfectly flat against the chest. Without a heavy 100% cotton substrate, any advanced print technology applied later lacks the physical anchor required for high-fidelity results. Once the microscopic physics of the fabric are locked in, we have to look at the macro geometry of the pattern cut. The dropped shoulder silhouette is a deliberate architectural choice, distinct from merely scaling up a standard size. This spec sheet details the raw dimensional data required to build this specific technical silhouette. Notice the exact geometry here for a size medium, a precise 22-inch body width intersecting with a 27-inch body length. Compare this specialized width-to-length ratio against a standard tubular t-shirt block, which is essentially a straight cylinder with no three-dimensional articulation. When you pair this dropped shoulder geometry with the heavyweight cotton we just analyzed, you get a very specific functional result. The wider ratio forces the heavy fabric to drape cleanly away from the torso rather than clinging to the skin. This drape creates a permanent gap of negative space. It provides structural volume to the wearer while maximizing internal airflow during movement. If you applied this exact geometric pattern to a lightweight poly blend, it would result in a sloppy, collapsing silhouette with zero structure. The pattern architecture dictates exactly how the engineered fabric will perform and survive in three-dimensional space. With the fabric and pattern locked, we reach the final layer of the triad, the chemical application of the graphic. This graphic schematic displays the extreme high-fidelity demands of modern cyber-aesthetic designs. It requires rendering razor-sharp vector lines, fine internal details, and perfectly spaced symmetrical elements. Historically, traditional screen printing has been the industry standard for apparel graphic application, but screen printing has a hard mechanical limitation. You have to burn a separate physical screen for every single color used in the design. When you attempt to recreate complex, multicolored gradients using this method, you end up stacking physically heavy layers of plastisol ink on top of each other. Traditional screen printing cannot meet these specific weight and flexibility tolerances while maintaining the necessary resolution for this aesthetic. This bottleneck requires a technological upgrade: direct-to-film and direct-to-garment printing. The primary advantage of this process is the ability to process full-color digital gradients and photographic fidelity with 0 per-color setup limits. Direct-to-film printing works like this. The design is printed onto a PET film using water-based inks. A powdered adhesive is applied to the wet ink. During heat curing, a press melts the adhesive, fusing the ink directly into the underlying fabric fibers. This specific thermal bond allows us to control 3 physical parameters of the print: graphic thickness, stretch flexibility, and surface texture. Because we are pressing this melted adhesive directly into the highly porous cotton Omi established earlier, the graphic maintains a natural hand feel. This deep bond results in superior stretch recovery. The graphic can expand and move with the heavyweight drape of the shirt without cracking or peeling under tension. Direct-to-film is the only application method that preserves the substrate's architectural drape while delivering infinite graphical resolution. When these layers converge, the cotton weave locks into place, the oversized seams stitch together, and the high-fidelity graphic fuses to the chest. The result is a functional triad: heavyweight cotton, a dropped shoulder cut, and high-fidelity digital printing working in concert. The system remains fragile. Compromising on any single pillar destroys the performance of the other two. But when aligned correctly, you get the fully realized iteration of this system, a piece of clothing built to endure. Technical streetwear quality is defined by the invisible engineering that supports the aesthetic.